Now let's consider the difference. Okay, I think I can erase the theorem now. You know the meaning of the theorem. I need some scratch paper to figure out. I need to check if f of x minus f of x0 is less than epsilon for x minus x0 less than some delta. I need to find this delta. I need to find a delta so that x close to x0 in terms of delta, then f of x close to f of x0 in terms of epsilon. That's equivalent or necessarily sufficient condition for continuity, remember, so that's a continuous. We'll prove this theorem. So we want to use that. So I need to show that these two are close when these two are close. I need to show this delta exists. Okay? Now how to do that? What I know is that f is the limit of a sequence. This is the limit of sequence. So this one is less than or equal to, by triangular inequality, minus fn of x plus, or maybe that's equal to, okay, plus fn of x minus fn of x0 plus fn of x0 minus f of x0. Right? I just have minus fn x plus fn x minus fn x0 plus fn x. Okay? The idea is this. I want to compare fx and fx0. But I do not have immediate information about these two functions. I don't know these two functions. All I know is that these two functions are limit of a sequence. So what I can do, the best I can do is link this expression into with the sequence. That I know something about it. All right? So that's the, now this is less than or equal to f of x minus fn of x plus fn of x minus fn of x0 plus fn of x minus fx0 n of x. I want to make sure that these all, if I want to show this is small, I need to show that all the three can be arbitrarily small. Okay? Now this can be small because f of x converts to f of x, fn converts to f uniformly. So this can be uniformly small as long as n is large enough, right? And this can be small. That's really because if x is close to x0, then this will be small because fn x is continuous. We know fn, each term is continuous. So if x is close to x0, then this is small. Now this is small, that's also because fn converts to f. So this three, all the three can be small. All right? But we still need to be a little bit careful because what is n then? What is n? Actually, all I need is a delta. I don't need an n. All I need is, to prove this is continuous, I need a delta. That's it. Okay? But I cannot get delta directly. I need to borrow an n. But which n I want to borrow? I just need one n is good enough. Okay? Now I need to borrow one fn that is n is large enough so that this is small enough. Okay? So we know that there exists a capital N so that fn of x minus f of x less than epsilon over 3 for all the x in R. Actually, for all the n bigger than capital N, I have that, but I don't need it. I just need one fn. That's it. As an intermediate tool, I need only one fn. So let's choose one so that is because of uniform convergence, right? If uniform convergence means that there's n so that any term after the capital N, the difference is less than whatever epsilon for arbitrary x. Okay? So I just choose that n. Okay, choose one n. Now for this particular fixed n, and there exists delta greater than 0, so that fn of x minus fn of x0 is less than epsilon over 3, so that x minus x0 less than delta implies. Now for this term, if you fix capital N, that's continuous function, right? For each fixed capital N, for each fixed n, the f of nx is continuous. So that's a continuous function, so I know that this can be arbitrarily small if x is close to x0. Now for this one, because I have this, that's a special case of that, right? This is true for arbitrary x. Now this is just different for particular x, x0, so that's less than epsilon over 3, right? That's yeah. Now we combine this inequality together. What do we have? So the conclusion is that x minus x0 less than delta implies this now it changes to capital N. And this less than equal to capital N. Fix the capital N. I just need one capital N as my intermediate kind of a bridge to bridge the, to analyze the value. I just need one capital N. And for this N, we know this is less than epsilon over 3 because of uniform convergence here. This is less than epsilon over 3 because that each Fn of x is continuous, which is here. And then plus the third term is less than epsilon over 3. That's also because of this inequality, because the limit converges uniformly. Now I have this is. So now what will we prove? We'll prove the following. For arbitrary epsilon greater than 0, there is a delta so that if x minus x0 less than delta, this actually f x minus f of x0 equals to this, okay? This one is less than epsilon. So we prove that this function is continuous f x0. So now you can say that so f of x is continuous at x0. But x0 is an arbitrary point in I, so you can say that f is continuous over the interval I. So this theorem guarantees that if you have uniform convergence, then continuous function